Hello and welcome to another exciting episode of Advantest Talk Summit. Today, we're exploring the pivotal role of data management in the semiconductor industry. Data drives today's innovation in AI, cybersecurity, and more. Joining us is Joe Addiego, a seasoned executive with over 20 years of experience and leadership in IPOs, real-time systems, and software development. As an investor with In-Q-Tel, Elsoft Louis Partners, and Brave Capital, Joe has shaped markets for technologies like Aerospike and Crunchy Data, enhancing data management with low latency solutions and advanced analytics. Joe's been deeply involved in driving evolution of database as a service and also integrated data analytics, making him a true innovator in how we think about modern data infrastructure. He will be giving insights on the future of technology and the role data plays in shaping it all. Joe, welcome to the show.
Thank you, Don. So as Don mentioned, I have 20 years of operating experience as an executive and luckily participated in a couple of IPOs, one at Integrated Systems and one at Tellurian. Tellurian in particular was a data management company that focused on messaging applications in publish and subscribe. I'll talk a little bit about that later. And then I've done 25 years as an investor. I'm currently at Brave Capital, but I've been an investor at Elsoft Louis Partners and In-Q-Tel. And during that, I was the lead investor for a real-time database, Aerospike, that was used in the ad tech space and now has proliferated. We'll talk a little bit about that. At the time, the need that we saw as an investor was the need to guarantee low latency and low cost of ownership, along with being able to manage millions of transactions a second. I was also the lead investor in an open source Postgres company called Crunchy Data. And the early users there were the government, finance, manufacturing, and with an early implementation of Kubernetes. The system is used as a record for critical transaction systems. The system has now evolved into one that allows for database as a service, as well as some very new news, becoming a data warehouse itself with data analytics.
Very impressive career, Joe. So before we talk about data management, where it is today, let's unwind and rewind a little bit, look at how it all started. So back in the days, managing data wasn't as easy or automated as it is now. We're talking about punch cards, tapes, and early file systems, things that laid the groundwork for everything we use today. As we're diving into the history of data management, why was it so important back then, and what are the challenges that people face and innovation that got us to where we are today?
The history of computing, I always see it as constantly moving upward in terms of the abstractions available. We've moved from assembly language to languages that were near the machine to things like Fortran and, now the eventual language, here we're speaking to machines through AI. So the things that followed those abstractions in processing, data management was also a function that followed those abstractions. So you talked about punch cards, for instance. I'm old enough that I started my career with punch cards. When I was in high school, I worked for the Treasury Department. We distributed hundreds of thousands of checks, and those checks to Social Security recipients were on punch cards. And those punch cards actually had data punched into them, and those were early databases. I would say the room that those punch cards existed was probably 2,000 square feet, and it was filled with cabinets filled with punch cards, and that was their data management. So we've moved from that to tapes to files and index files, and eventually then databases back in the 80s. And there were three types of early databases, hierarchically based, network, and relational. And really what these are trying to model is the relationship of data. So when the relationship can be modeled as a one to many, those hierarchical databases modeled that and allowed people to process through that. Network data enabled a many-to-many relationship. And so you can model that very easily in that database. And relational databases were based on a relational model that allowed you to view all of the data through relational algebra at the time. And while that was another abstraction, it led to the rise of a structured query language, which was known as SQL. And that language, you can see, it's been 40 years, and that language still is profuse throughout the industry. And the actual success and permanence of SQL is due to it being a declarative language rather than an imperative language. And a declarative language means that you don't define exactly the steps that you need to take in order to implement the command, but you would just define what the result is that you wanted. And the underlying processing would take care of itself. And I think that's one of the threads that we want to follow today. And that is, again, the rise of abstraction. SQL was abstracting the data away, the need to implement the data lookup away from the data itself. And that's why it was so popular. We'll follow that vector through time and see how, where we are today because of that. Another aspect of data back in the 1980s was that these became systems of record. They had to have something called ACID properties, atomicity, consistency, isolation, durability. Those properties, in essence, gave you a reliable system, a system that you can count on, that for any physical transaction to the database, you would get out what you put in. So you'd be able to read the data, and the data would be consistent. It wouldn't be corrupt. And if there was a problem, that all of the data would be backed out and the physical consistency of the database existed. So this is what I consider the prehistory of data management before the internet.
So Joe, now that we've explored the early days of data management, let's move forward to one of the most transformating period, the internet era. The rise of internet completely revolutionized how we manage, store, and share data. Suddenly, we went from local systems to a world of global connectivity where data can be accessed and shared in real time. This was also the era where the sheer volume of data exploded from megabytes to terabytes and beyond, driving the need for a faster, more scalable solution. It's the time where technologies like distributed system, NoSQL database, and real-time analytics started shaping the future. In this segment, we'll dive into how the internet era changed the game for data management, the role semiconductors played in supporting this shift, and how it laid the groundwork for data-driven world we live in today. To start, how do you think the internet fundamentally reshaped the way we think about managing data?
Well, I think before we get to the lessons that would apply today, we should talk about the internet era. The internet era really had a huge change to data management. Hegel, a German philosopher, and he said a change in quantity creates a change in quality. And what you had with the internet era is a very dramatic change in the quantity, the speed of which those transactions were coming at you, the volume of transactions coming at you, and the variety of the transactions coming at you were all exceedingly much larger than prior to the internet era. And so that really drove a lot of changes in the data management space. Let's just talk about some of those. So there was a tremendous need for speed, making databases go faster. One of my earliest jobs was helping to sell hardware. And I recall doing mini computer performance reviews, and we were talking about 30 reads or writes per second, 30 database transactions per second. The internet era brought that number up tremendously. And as I mentioned, one of my investments was Aerospike. Aerospike now does, close to a cluster will do 3 million transactions per second. Billions of transactions per day are required for this. And there were a huge amount of changes necessary to do that. So restructuring the internals of the database. We went from simple B trees to log structured merge trees. We added caches on the front ends so that the data would be filled with memory first. And then there was a rise, as I said, in real-time databases such as Aerospike. So the creation of databases focused on real-time and large amounts, high volumes, enabled the ability to approach, things like Twitter, what is needed for, applications like Twitter. Scale, for instance, the scale from megabytes to terabytes and beyond, you needed to go to distributed data architectures in order to enable that. You had to put caches in front of systems and distribute the data across that. Data variety. What happened is photos, videos, documents, large objects were now stored rather than just transaction-oriented systems. So let me give you an example from an early investment that we made, a company called CleverSafe. As you recall, in the dawning of the phones, where a phone became a camera, as well as your computer that you carried along with you with all your apps. That necessitated the requirement for a lot more storage. All the photos that everybody was taking had to be stored someplace. So CleverSafe, an early investment for us, developed a distributed object storage system. They distributed that data across a plethora of servers all across the internet. They encrypted that data securely and also sharded that data in such a way that only pieces of the data would be on any particular server, but you could recover the data with only a subset of the servers that you had posted the data to, because it had a networking concept called feed-forward information also included. So there was a little bit extra amount on each server, so you didn't need to recover every server. That is the only way that you could really securely store billions of photos on the network as is stored now. And if you look at, IBM eventually acquired CleverSafe for billions of dollars. So that was it was a successful investment, but also it enabled, it showed a new paradigm required for data management. The NoSQL databases were also a key when these changes were happening because of the internet. I mentioned the fact that document storage is something that came out of the need for data variety. Key value storage, that was the Aerospike database. Tabular storage, Cassandra. Wide column, Google's Big Table. Graph databases, time series databases. What you had is a proliferation of databases for the wide variety of data that you needed to store. The architecture of an application changed considerably. From a single transaction database that sat at the core of an application, what you now had the front ends, either caches or real-time databases. You had your system of record transaction databases still at the core of an application, but you also had a document database like MongoDB that you connected to to store those objects, your JSON files. And that enabled you to deal with this plethora, of different kinds of information. So a single database was no longer sufficient. Well, given that that was what the application looked like, you now also had to have a messaging system to pass that data between each of the different components that you had. So as I mentioned, I was at Tellurian. That was a publish and subscribe messaging system. In the early days, the folks that used those things were mostly in the financial community. For instance, if you look at the Philadelphia Stock Exchange, the one that deals with options, every one time, if you have a movement in the change in a price of a stock, there really isn't that much data in a transaction if it's just that particular data that you're worried about, the change in price. But if you have options, puts and call options, and you have them for many different dates, the amount of data that has to change when there's a change in price is very dramatic. And at Tellurian, we were very successful, for instance, with the Philadelphia Stock Exchange and the Chicago Stock Exchange. And given that we were able to handle these very high transaction volumes, we eventually then became the system for the American Stock Exchange and the NASDAQ as well. So, it showed that, there was a need to move data. Messaging queues were another approach at messaging systems where you queued data in. And then, of course, with an application running, you needed streaming data services, and Kafka was developed. Overall, an application itself would go, now having from one particular database to many, and the need to move all that data around. In addition to that, there was the need then to analyze the data, generally not in real time. There were a need to do analytics or business intelligence on that data. At the same time as this data proliferation was happening, you saw large data systems also rising and changing. So early systems in that era were things like Teradata and Greenplum, that these data warehouses had very specific architectures that were necessary in order to help to manage very, very large pieces of data. But with the internet, what happened is people were able to use standard hardware and use just new data management approaches and distribute that processing. And the early view or the early vision of that, the early instantiation of that was really Hadoop. So Hadoop came with the Hadoop file system. It came with a method in order to process that data, MapReduce, and ways of accessing it, Hive. So now, not only did you have your application, which had several databases, but then it had another system, usually with something like ETL to process the data between the application in batch, and then that system sat behind it, and it was generally a non-real-time system where you would do a data analysis. We'll talk about how, because of changes in hardware and the evolution of software, that these systems are being drawn back. We'll talk about a specific use case in the semiconductor industry where real time is advantageous. So you want to do your analysis much closer to the time when the data is flowing into the system. But there has been an evolution even in the analytics space as well, moving from Hadoop to Parquet, Iceberg, and larger independent systems like Snowflake and Databricks based on Apache Spark.
So I'm curious, how did the rise of distributed systems and real-time databases pave the way for today's AI-driven innovation?
Those systems, enabled the AI systems because they made high quality data available for training. What you're going to see now in today's world with AI, LLMs rely on well organized, very high quality data and the need for these data pipelines because the LLMs are based on petabytes of data for training. So what you've seen is the kind of that movement towards very large data sets has continued, and it is now a necessity for LLMs using AI for training database. Another thing that's happening, another new pattern in the database world that's happening today because of AI is the addition of a vector database. In order to do a similarity search, you really need to change the representation, or you need to convert that raw data that you have of text, images, audio into a vector representation. And if you do that vector representation using the same embedding model that an application that you have and that's important to you uses, you can then use that data and do a similarity search based on that vectorized data. And that is used quite often for systems that do what's known as retrieval augmented generation, or RAG applications, so that you don't have to go back to the LLM for the local data that you're mostly concerned with. So your systems would vectorize your own data, put it into a vector database, and then use an application and directly search that prior to going back to an LLM. So what you're seeing is the integration of yet another database into the data model. The actual need, as I mentioned, for variety, velocity, the fact that the data was needed to scale to such large extent with much faster performance, and that there was a variety of data. So they often talked about it as the 3 V's: variety, velocity, and volume. That forced changes in the way that you had to manage the data.
So, and then we're leaning into the data today and also Gen AI. So we've talked about how data management evolved from the early days to the internet era, and now we're into a whole new phase where data isn't just stored and managed, but actively drives some of the most advanced technology we have ever seen. Generative AI, and along with other AI and machine learning technologies, relies on massive amount of high quality, well-organized data to function effectively. So exploring into why data is considered the lifeblood of AI, the challenge of managing data at such a massive scales, and how industry like semiconductors are already applying generative AI to solve real-world problems. So let's look into why is data so essential for technologies like generative AI and other AI ML models.
As we mentioned, it's really the fact that AI relies on data. Data is used, to train these AI systems, and they need to rely on a large amount of high quality data. We're talking about petabytes of data to train the LLMs that exist right now.
We mentioned a lot about data quality. So can you explain a little bit on what role does data quality and organization play in successfully training the large language models, the LLMs?
Basically, there's been a rule in the data management space for many, many years. It was called GIGO, and that is garbage in, garbage out.
Yes.
That still applies 50 years later. So that if when you're training LLMs, you've really basically, you want to train it. The data has to be It's not as important actually for AI systems because the neural networks actually, can train just based on data itself. In machine learning, it's especially important. You've got to label data correctly, and there's a lot of data engineering that's required in machine learning. And so you have to really label data correctly, and the data needs to be applied. You have to do engineering, function engineering, to understand what it is that the machine learning algorithms are going to provide for you.
Yes, and we read a lot about the hot ChatGPT and OpenAI spending a lot of effort, a lot of resources on trying to curate their data and making sure that data is clean, accurate, and free of bias. How do companies ensure data quality, traceability, and compliance as their data set grow in complexity?
There are new governance frameworks that are focused on building that. There is an entire focus on data management now that is working with frameworks that work with the metadata in order to provide that quality, traceability, and compliance.
So we also talk about, AI is requiring data and training a lot on data. So what steps are being taken to secure AI training data and ensure that it's protection during the processing so we're not losing our data, we're not leaving our data out there for other people?
With the fact that there is a lot of data that's now used, the security model has changed. So the security model now has to focus on your data. I mean, it always has been important, but a way to change the training weights for AI would be to pollute the initial data. So the security models now really have to take into account what is happening with the training data. Let's talk about, for instance, what security models currently exist. You've got right now data in transit secured. You also have data at rest secured. So while the data is on your disk, it's secured. What you're looking at in the future is that you want to secure the data in memory and compute. That is right now an opening. And, in addition to that, you would like to be able to share data between AI and ML systems and with other members of a team, but you want to maintain data privacy. There are models for that are just emerging right now, and I can introduce those to you.
We'd love to hear about that.
Okay, so one of those is confidential computing. Confidential computing provides a trusted environment, a trusted execution environment for a secure enclave. It's not just hardware security module for the cryptographic keys that you're used to, but it's an enclave where the encrypted data would come into. The keys would be managed within that encrypted enclave. The data is then unencrypted while it's in the enclave. It's not available. It was encrypted while it was in memory. It then is also computed in an unencrypted form. And then before it is put back to memory and before any of the results are put back, those are also encrypted. And interestingly enough, there's also an attestation process that forces the enclave to define that it is a secure place for you. So this system would allow for data to be secure all the way through, from transit to rest through processing. And it would enable the training data to be maintained in an encrypted form. It would enable the weights to be maintained in an encrypted form. And if you used it in an inference system, the weights would be encrypted until they're used, and the data would be inferenced in an encrypted approach. So it gives you a full cycle of encryption. And I think that that is what we're going to be looking at in the future. Some of the benefits of it allow, it prevents unauthorized access, even by administrators. It provides regulatory compliance. And it also enables multi-party data sharing while maintaining data privacy. You can have people share different data sets. The system could then compute that and keep the data private across all of the different areas. So I think that we're looking at the future there for what's going to happen with data management. So it's going to add the extra aspect of being able to be managed and managed securely throughout its life cycle.
That's fantastic because as we talk about in generative AI and also in semiconductor world, we keep talking about there's the need to share data across different companies, across different players, especially in the semiconductor industry as we're approaching 2 nanometer and Armstrong. There's a lot of challenges. There's the need for us to share data, but the key concern for a lot of players is losing our IP. So we want to share data with each other, but we don't want to lose our IP. So it sounds like confidential computing with all its potential could be a solution for us. Would you agree with that?
Oh, absolutely. In the semiconductor testing space, there's been a data format called Standard Test Data Format, STDF. It's a standard file for storing test information, lot information, and the semiconductor test results. The latest version is version 4 out of 2007. As you can see, that would be equivalent to one of the prehistory. Advantest and Synopsys did a strategic development a couple of years ago, and you introduced something called ACS, which is Advantest Cloud Solutions Nexus.
Yes.
That system connects through the cloud in a real-time basis. So it will do that, designed for outsourced semiconductor assembly and test. It will connect various outsourced assembly and test vendors throughout the world together, and it enables automated data streaming via an API in real time. You can then apply real-time analytics to that data, and over time, what you'll find is there will be people that will want to connect those analytics and do machine learning and do AI on that data, but they will want that data to be private to their particular systems. And that would be the case for the confidential computing. So you've seen Advantest kind of move from these file-based formats, moving to the cloud, to real-time streaming, to AI, and in the future, potentially confidential computing. All of this would then, take this view of improving yield, cost savings by reducing retests, and providing better quality. So and streamlining the data management processes for the various companies that are actually doing the testing. So this is an example of how, data management improvements through time are being applied everywhere, including the semiconductor test equipment space.
How do you see data management practice evolving to support future AI innovation?
As we said, I think what you're going to see is there's going to be more. We now have many different systems available. And as often happens, you go through a proliferation, and then there's a time for everything to kind of be pulled back in together. So you've seen, just the Postgres company that I talked about that we are an investor in, Crunchy Data. They have a system of record transaction system, but they just released an analytics warehouse. And now your SQL queries can be applied to the transaction data, and you can also get analytics data immediately from that. So what you're seeing is a kind of a reintegration of all the different pieces that have been scattered about. The people now, what happens is when you have to have many different pieces and data managed through them, all of the messaging that happens, you allow for the data to be inconsistent throughout the system. And there is a view that to the extent that you can remove the potentials for inconsistency, you're much better off. So you're looking at a much tighter reintegration of data in the future, I believe.
Joe, throughout this conversation, we've explored the history of data management, its evolution through the internet era, and how it powers cutting-edge technologies like generative AI today. As we wrap up, I want to shift our focus to the present and future. So data management continues to evolve rapidly with trends like cloud adoption, edge computing, and confidential computing, shaping how organizations operate. For companies, the big question now is how do they turn their data into a competitive advantage while staying secure and scalable? So we'd like to dive into the latest trend and cover opportunities for innovation and get your advice for companies navigating challenges like data growth and cybersecurity. So let's start with this. What are some of the biggest trends you're seeing in data management today, and how can businesses prepare for what's coming?
I think we've mentioned some of them, but again, I'll go back to this reintegration of data. That's one of the things that I see right now, data being integrated so that the silos of data that people have are brought together. So the data analytics is being moved closer and not allowed to get out of sync with data that exists in the transaction systems. That's, I think, the largest focus. And then the next focus is basically security that's going to be applied across the data realms.
How should businesses approach integrating new technologies like confidential computing into their strategies?
Well, one of the unique aspects of the confidential computing is that it is not a lot of lifting to do. That it's more a function of whether or not the hardware has adopted that, and whether or not you have all of the people in place that can put that together. Many of these systems don't require recoding, luckily.
Looking ahead, what do you think will be the next major breakthrough in data management, and how should companies prepare?
Well, that's a very good question. Other than what we have talked about in terms of the integration, the confidential computing, I'm not really sure what the next breakthrough will be.
Joe, thank you so much for joining us today and sharing your incredible insights from the early days of data management to the transformative impact of internet and now the cutting edge role of AI and generative AI. Your perspective has been inspiring. For our listeners, if you are as fascinated by today's discussion as I am, don't forget to subscribe, leave a review, and share this episode with anyone who's interested in the evolving world of data and technology. So Joe, before we wrap up, any final thoughts or advice for our audience as they navigate the future of data-driven innovation?
No, I think we've discussed many different aspects, and I think the future is one where the data will continue to proliferate, and you'll need to secure your data much more than you do today.
I'm excited about that, and also for what's coming with confidential computing. Thank you so much, Joe.
Thank you, Don.